When Oumuamua was first detected, tumbling through our solar system in October 2017, astronomers thought they understood what they were looking at: an interstellar asteroid, the first ever confirmed visitor from beyond our sun's gravitational influence. Unusual, certainly. Historic, absolutely. But fundamentally explainable within our framework of planetary science. Then the data started coming in. And with each new measurement, each refined analysis, each peer-reviewed paper, Oumuamua became stranger. Its shape defied expectations. Its surface properties made no sense. Its acceleration violated physics as we understood it. And now, 7 years later, after thousands of hours of analysis and dozens of competing theories, we're further from understanding what Oumuamua actually is than we were the day it was discovered. The more we study it, the more alien it becomes. The story begins on October 19, 2017, when Robert Varick at the University of Hawaii spotted an unusual object in Pan-STARRS telescope data, a faint point of light moving against the background stars. Initial observations suggested a near-Earth asteroid, unremarkable except for its speed, but within 24 hours, trajectory calculations revealed something unprecedented. The object was moving at 87.3 kilometers per second on a hyperbolic path. It wasn't orbiting our sun. It was passing through from somewhere else. For the first time in human history, we detected an object from interstellar space, while it was still close enough to study. Astronomers mobilized every available telescope: the European Southern Observatory in Chile, the Gemini Observatory in Hawaii, the Keck telescopes, Hubble Space Telescope, even radio telescopes searching for any signals. Everyone wanted data before this visitor disappeared back into the void, and what those observations revealed would fuel debates that continue to this day. Before we examine each anomaly that makes Oumuamua increasingly inexplicable, make sure you're subscribed to Cosmic Outliers and notifications are turned on. This is one of the most controversial objects in modern astronomy, and the mystery keeps deepening. Drop a comment with what you think Oumuamua really is, because by the end of this video, you'll understand why there's no consensus answer. The first strangeness emerged from photometric observations. As Oumuamua tumbled through space, its brightness varied dramatically over a period of 7.3 hours. Not unusual for asteroids, which often rotate and reflect different amounts of sunlight depending on their orientation. But the magnitude of Oumuamua's brightness variations was extreme. At its brightest, it was about 10 times brighter than at its dimmest. This suggests an elongated shape, something like a cigar or possibly a flat disk, depending on viewing angle. Astronomers calculated an aspect ratio, the ratio of longest dimension to shortest, of at least 6:1, possibly as high as 10:1. Nothing in our solar system looks like this. The most elongated asteroids we've studied have aspect ratios around 3:1. Elongated shapes typically result from collisions that fragment larger bodies, or from tidal forces stretching objects during close planetary encounters. But objects with extreme elongation are structurally unstable. Their own rotation creates stresses that should cause them to break apart over time. For Oumuamua to maintain a 10:1 aspect ratio while tumbling at observable rates requires either very recent formation, meaning it was created relatively shortly before entering our solar system, or unusual structural strength from materials or internal configurations we don't expect in natural asteroids. Spectroscopic observations added more confusion. When sunlight reflects off an object's surface, the reflected light carries signatures of surface composition. Different minerals absorb specific wavelengths, creating absorption features in the spectrum. Oumuamua's spectrum showed it was red, similar to many outer solar system objects that have been exposed to cosmic radiation for billions of years. This reddening comes from organic compounds, carbon-based molecules created through radiation processing of simple ices and hydrocarbons. So far, consistent with a natural object, but the spectrum lacked water ice features. Most comets and many asteroids from the outer solar system show clear signatures of water ice. Oumuamua appeared dry. This was the first hint that Oumuamua didn't fit standard categories. It looked like an asteroid in some ways, lacking the coma and tail typical of comets. But asteroids don't usually come from interstellar space with hyperbolic orbits. Objects ejected from other planetary systems during formation are more likely to be comets, icy bodies from outer system regions where ejection is more common. Yet Oumuamua showed no cometary activity, despite passing within 0.25 astronomical units of the Sun, closer than Mercury's orbit. where solar heating should vigorously sublimate any surface ices. Then came the acceleration anomaly. As astronomers tracked Oumuamua's position over weeks, they noticed something impossible. The object was accelerating away from the sun faster than gravity alone could explain. The deviation was small, about 0.0001 meters per second squared, but measurable and confirmed by multiple independent teams. Something was pushing Oumuamua off its gravitational trajectory. For comets, this is normal. Outgassing creates rocket-like thrust, but Oumuamua showed no outgassing, no coma, no tail. Even the most sensitive observations detected no gases being released, yet it was accelerating. This single fact has driven more scientific debate than perhaps any other astronomical observation in recent years. How does an inert object accelerate through space with no visible propulsion? The scientific community proposed numerous explanations. Perhaps Oumuamua was outgassing, but the material was something our instruments couldn't detect. Pure molecular hydrogen, for example, would be nearly invisible in standard observations. A team led by Dr. Jennifer Bergner at UC Berkeley published a paper in 2023 suggesting that cosmic rays striking water ice during interstellar travel could create trapped hydrogen molecules. When Oumuamua warmed near the sun, this hydrogen could be released gradually, producing thrust without visible coma. The model was elegant and relied on known physics, but it required very specific conditions. The ice composition had to be just right. The cosmic ray exposure had to last long enough. The warming had to proceed at exactly the right rate. Critics argued these requirements were too fine-tuned, explaining one mystery by invoking several unlikely coincidences. Another explanation involved Oumuamua's shape. If it was extremely thin and light, like a disk or sail less than a millimeter thick, radiation pressure from sunlight could produce the observed acceleration. Dr. Avi Loeb, chair of Harvard's astronomy department, calculated that a sufficiently thin, low-mass object would be pushed by photon pressure strongly enough to match observations. He suggested Oumuamua might be a light sail, either a piece of advanced technology or debris from such technology. This proposal generated intense controversy. Most astronomers favored natural explanations, arguing that invoking artificial origins without exhausting natural possibilities was premature. But Loeb countered that the artificial hypothesis should be evaluated on its merits like any scientific proposal, not dismissed because it seems unlikely or uncomfortable. The debate revealed deep tensions about how astronomy should approach anomalous objects. The default position has always been naturalistic. Assume natural phenomena until proven otherwise. But what constitutes proof? And at what point does accumulated anomalies make natural explanations less plausible than alternatives? These questions don't have clear answers, and Oumuamua sits exactly at that uncomfortable boundary. Additional observations made things worse, not better. Thermal modeling of Oumuamua's surface temperature, based on its distance from the sun and assumed composition, predicted one set of values. Actual measurements from infrared observations showed different temperatures. The surface was cooler than expected for a dark, rocky object. This could mean higher reflectivity than brightness measurements suggested, or it could indicate unusual thermal properties. Neither option fits perfectly with other observations. High reflectivity contradicts the object's overall darkness. Unusual thermal properties require explaining what materials would behave that way, and why we've never encountered them in solar system objects. Rotation state analysis added another puzzle. Oumuamua's 7.3-hour tumbling period is relatively fast for an object of its estimated size, somewhere between 100 and 400 meters in longest dimension depending on assumptions about shape and reflectivity. Fast rotation usually indicates recent disturbance from a collision or tidal encounter. But Oumuamua has presumably been traveling through interstellar space for millions of years. During that time, internal friction and other damping mechanisms should have slowed its rotation significantly. The fact that it's still tumbling fast suggests either it experienced a collision relatively recently in astronomical terms, perhaps within the last few million years, or its internal structure resists normal damping processes in ways we don't understand. Attempts to determine Oumuamua's origin by tracing its trajectory backward through the galaxy have been only partially successful. The path points generally toward the star Vega, in the constellation Lyra. But Vega wasn't in that position when Oumuamua would have passed through that region hundreds of thousands of years ago, accounting for stellar proper motion. The object's true birthplace remains unknown. Computer simulations show it could have come from any of thousands of stellar systems depending on uncertain variables like exact velocity and the gravitational influences it experienced during its journey. We know it came from somewhere else, we know it's been traveling for a very long time, but we can't identify a specific home. The size uncertainty compounds every problem. All size estimates for Oumuamua rely on measuring how much sunlight it reflects and assuming a reflectivity value. If the surface is highly reflective, the object is small. If it's dark, it's large. This uncertainty propagates through every calculation. Mass estimates depend on size and assumed density. Structural strength calculations depend on mass and shape. Thermal predictions depend on surface area and composition. Everything connects to everything else through assumptions that can't be independently verified because the object is too small and too distant for direct imaging of surface features. Perhaps most frustrating is what we missed. Oumuamua was discovered when it was already leaving the solar system. We had only weeks of observation before it faded beyond detection limits. Most measurements were made after the object had already rounded the sun and was heading back toward interstellar space. We completely missed its inbound journey. If it showed different behavior approaching the sun versus leaving, we'd never know. If it activated some process during close solar passage and then went dormant, we'd only see the dormant state. The observational window was narrow, and we weren't prepared. When the detection happened, no missions existed that could be rapidly redirected for intercept. The object was moving too fast for any spacecraft to catch up using current propulsion technology. We could only watch it leave. In the years since, analysis has continued using archived data. Every telescope observation, every spectroscopic measurement, every photometric data point has been scrutinized and re-scrutinized. New papers continue to be published proposing alternative interpretations or refining previous models. But consensus remains elusive. The scientific literature contains multiple incompatible explanations for Oumuamua's properties, and adherents of each explanation point to different subsets of the data that support their view while explaining away inconsistent observations. This situation is unusual in modern astronomy. Typically, as more data accumulates, competing theories are winnowed down until one emerges as clearly superior. With Oumuamua, more analysis has produced more disagreement. Each research group emphasizes different anomalies as most significant. For some, the acceleration is primary, and everything else is secondary. For others, the shape is the key puzzle. For still others, the lack of outgassing despite acceleration is the central mystery. And some argue we're missing something fundamental, that all the anomalies are symptoms of a single underlying strangeness we haven't yet identified. The possibility that Oumuamua is artificial technology remains controversial but hasn't been definitively ruled out. Loeb's Galileo project, launched in 2021, aims to search for evidence of extraterrestrial technological artifacts by improving detection and characterization of anomalous objects. The project operates under the principle that absence of evidence isn't evidence of absence, and that science should actively look for signs of technology rather than assuming all anomalous observations have natural explanations. Critics argue this approach risks pattern matching and confirmation bias, finding significance in noise. Supporters counter that we'll never find evidence of other civilizations if we don't look seriously and systematically. Public reaction to Oumuamua has been mixed. Media coverage often emphasized the alien technology angle because it makes compelling headlines. This frustrated many astronomers who felt the sensationalism overshadowed legitimate scientific investigation and made serious researchers seem less credible. But the coverage also captured public imagination. Oumuamua became a cultural touchstone, referenced in science fiction, discussed in podcasts, analyzed by enthusiasts. The term Oumuamua entered popular vocabulary as shorthand for mysterious object from space. Whether this attention helps or hinders scientific investigation is debatable. What's clear is that Oumuamua exposed gaps in our understanding of interstellar objects and their properties. Before 2017, we had theories about what interstellar visitors should look like, based on models of planetary system formation and ejection mechanisms. Oumuamua matched almost none of those predictions. It was the wrong shape, the wrong composition, showed the wrong behavior. This forced a reckoning. Either our models were incomplete, missing processes and outcomes that occur in nature but hadn't been accounted for theoretically, or Oumuamua is genuinely exceptional, a rare object formed under unusual circumstances that we happened to detect during our first confirmed interstellar visitor. Subsequent interstellar objects have complicated the picture. 2I Borisov, detected in 2019, behaved like a normal comet, matching predictions and showing unremarkable properties. This suggested Oumuamua might be the outlier, but then 3I Atlas and other recent detections showed various anomalies, none identical to Oumuamua, but all deviating from expectations in different ways. The emerging pattern is that interstellar objects are diverse, more variable than solar system bodies, possibly because they sample a wider range of formation environments and evolutionary histories. If true, this means Oumuamua might not be a unique mystery, but rather the first example we encountered from a population of objects with properties outside solar system norms. The question of whether Oumuamua is alien depends on how you define alien. If alien means originating from outside our solar system, then yes, definitively, it's alien. It came from interstellar space, formed around another star, carries chemical and physical signatures of formation in a different planetary system. In that sense, every interstellar object is alien, visiting from foreign stellar environments. But if alien means artificial, created by intelligence, then the evidence is ambiguous and insufficient for conclusion. Nothing observed definitively requires technology as an explanation. Everything could potentially be natural, given sufficiently exotic but physically plausible conditions. But neither can technology be ruled out. The observations don't exclude that possibility. This ambiguity is where we remain 7 years after discovery. Oumuamua exists somewhere in the uncertain space between clearly natural and potentially artificial, exhibiting properties that challenge our models while not quite breaking them completely. It's anomalous enough to generate controversy, but not anomalous enough to force paradigm shift. And that's perhaps the most alien thing about it. Not that it might be technology, but that it exists exactly at the threshold of our ability to categorize and understand it. The legacy of Oumuamua will likely be methodological. It revealed that we need better detection systems to find interstellar visitors earlier, while they're still approaching, and we have time to prepare detailed observations or even launch intercept missions. It showed that we need rapid response capabilities, telescopes, and spacecraft that can be quickly redirected when targets of opportunity appear. And it demonstrated that we need more sophisticated models incorporating a wider range of possible compositions, structures, and behaviors, because the universe clearly produces objects our theories didn't predict. Several space agencies are developing concepts for rapid response missions. The idea is to have spacecraft in standby orbits, fueled and ready, waiting for the next interesting interstellar visitor. When detected early enough, the mission could launch within weeks and conduct a flyby or even rendezvous, providing close-up data that remote observations can't match. The technical challenges are significant, and funding is uncertain, but the scientific justification has been established. Oumuamua showed us what we miss when we can only watch from afar. As for Oumuamua itself, it's now far beyond any telescope's reach, more than 7 light hours from Earth, and receding at over 26 kilometers per second relative to the Sun. In a few 100,000 years, it will pass near another star system. If that system hosts observers and if they detect it, they'll measure the same puzzling properties we did. Perhaps they'll have better instruments or different theoretical frameworks that allow them to understand what it is, or perhaps they'll be just as confused, adding their own observations to the mystery without solving it. The object that taught us we don't understand interstellar visitors as well as we thought will continue its journey through the galaxy, carrying its secrets with it. If this deep dive into why Oumuamua becomes more alien with every analysis resonated with you, hit that like button and subscribe to Cosmic Outliers for more investigations into cosmic mysteries that resist easy explanation. Drop a comment with your theory about what Oumuamua really is, because this is the kind of question that reveals as much about our assumptions as it does about the object itself. The more we study it, the more questions emerge. And perhaps that's the real message Oumuamua delivered. The universe contains things we're not yet equipped to fully understand.